Hello everyone, this is SAVITHA Acharya from Canara Engineering College. In this video lecture, we will deal with gate delays. So far, we have realized various digital circuits using logic gates in Verilog, but never we have associated any delays with these gates. But actually in real circuits, the logic gates have delays associated with them. Verilog allows you to model these gate delays in the program. Okay, this is by specifying the delays through the logic in the program itself. Basically, there are three types of delays from the inputs to the output of a primitive gate, categorized as rise delay, fall delay, and turn off delay. The rise delay is defined as the time taken by the gate output to reach a value of 1 from any other value. So we have seen that Verilog signals can take by default 4 values, that is 0, 1, X and Z. So rise delay is defined as the time taken by the output of a gate to reach a 1 from 0, X or Z. Similarly, the fall delay is defined as the time taken by the output of a gate to reach a value of 0 from the other three values, that is 1, X or Z. Likewise, the turn-off delay is defined as the time taken by the output of a gate to reach a value of high impedance from any other values. In case the value changes to X, the minimum of the three values is considered. Now these value delays are actually applicable to any signal as they all can rise or fall anytime in real circuits and are not restricted to only outputs of gates. Let us look at a few examples for rise, fall and turn off delays. Now delays can be specified as a single delay or two delays or all three delays may be given. Now here let us take the first example. So and this is a instantiation line, that is and is the name of the primitive gate in Verilog, followed by the delay. So far we have just instantiated the gates without specifying the delay. Now that we have come to this topic, so delays are, note that delays are specified using a hash and in brackets the value of the delay. So here only one delay is specified, followed by here A1 is given. A1 is the instance label as usual, and as we know for primitive gates, first terminal should always be the output followed by the inputs. So here we have out I1, I2. So this is an instantiation of a two input AND gate. Okay. So since only one delay is specified, so for all the three types, that is for rise, fall as well as turn off, this 5 is taken as the delay. Next example is where we specify two delays. So again I take AND hash 4,6 is two delays are specified here. A2 is the instance label out, I1, I2. So here the first delay specified is always the rise time, rise delay, that is 4, and the second one is the fall delay, that is fall delay is 6. And when in case where only two delays are specified, the minimum of the two are taken as turn off delay. Okay, so turn off will be the minimum of 4,6, that is 4 will be the turn off delay. Last example is by specifying all the delays. So here we have taken the example of buff if 0. So remember buff if 0 has got three inputs, input, output and a control signal. So when control is 0 only, input will be transmitted to the output. If control is inactive, then that is inactive means if control is 1, then the output will be in the high impedance state. So here we have specified hash 3, 4, 5 in brackets, meaning rise delay is 3, fall delay is 4, and turn off delay is 5. As you know, B1 is the instance label, and here we all for buffers we first specify the output, then the list of inputs, that is input and next the control. For each of the delay that we have seen, that is the rise delay, fall delay and the turn off delays, there are three values can be specified, that is minimum value, typical value and maximum value. These values are important in modeling of digital circuits such that we have a range of minimum to maximum values because of the IC fabrication process variations. Okay, finally the digital circuits that we are realizing or modeling using Verilog have to go for fabrication. The end product is the IC which are fabricated in the foundries. So these foundries have got various process variations, and to adapt to these adverse conditions, we have this relaxation of a range of values. So minimum value is the minimum delay value that the designer expects the gate to have. Similarly, typical value is the typical delay value that the designer expects the gate to have, and finally the maximum value is the maximum delay value that the designer expects the gate to have. We'll look at a few examples of these delays, minimum, typical and maximum values. Recall that we have seen three types of delays, that is rise delay, fall delay and turn off delay. Okay, and these different delays we specify inside the brackets followed by a hash separated by a comma. Okay, so here if you see in this first example, I have AND hash 4 is to 5 is to 6, a bracket close, A1 is the instance label, out I1 comma I2. So this is an instantiation of a 2 input AND gate. Okay, so here the value that is given, so here if you note that only one type of delay is given. Okay, only one delay is given. So whenever there is only one delay specified, for all type of delays this same value is taken. That is for rise, fall as well as turn off delay, the same value is taken. So this colon indicates that the different values. So minimum, typical and maximum values. So this means that first one stands for minimum, second one is for typical and the last one is for maximum. So minimum value for all the delays, that is rise delay, fall delay, turn off delay, minimum value is to be taken as 4. Typical value for all three types of delays is 5 and maximum value for all three types of delays is 6. In this second example, two type of delays are specified. That is, if you see 3 is to 4 is to 5, comma 5 is to 6 is to 7. That means comma is there. So the two types of delays are specified and there are three values. That is minimum, typical and maximum values are specified for both these delays. So if you recall, when there are two delays given, the first one is the rise delay and the second one is the fall delay, and the turn off delay is taken to be the minimum of these two. Okay, so here the first value corresponds to the minimum value and this first delay is the rise delay, right? So minimum value of rise delay is 3 and minimum value of the second entity corresponds to the fall delay. So the minimum value of fall delay is 5. Turn off delay will be minimum of these two, that is 3 and 5. Okay, that will be 3. Similarly, Second, typical rise value is 4 and typical fall value is 6. So turnoff will be minimum of 4 and 6, that is 4. And finally, the last thing is for maximum value. This is the rise delay. So maximum rise delay is 5 and maximum fall delay is 7. Turn off delay will be minimum of 5 and 7, that is 5. Okay. The last example wherein all the three delays are specified. The first delay corresponds to rise time, rise delay. Second one is fall delay, and the last one is turn off delay. And for each of these type of delay, three values, that is minimum, typical and maximum values are specified. Okay, so minimum rise is 2, minimum fall is 3, minimum turn off is 4. Similarly, typical rise is 3, typical fall is 4, and typical turn off is 5. Maximum rise is 4, maximum fall is 5, and maximum turn off is 6. So this is how you interpret the delays and their types when given in an example. Now that we have seen different types of delays in digital circuits, that is rise delay, fall delay and turn off delay, and the various values they can take, that is minimum value, typical value and maximum value, we'll look into a delay example. Okay, we'll see an example and see the effect of incorporating this delay in our program. So here I have a simple combinational circuit. It consists of a AND gate and a OR gate. Okay, the circuit is D. The new thing here is there is something written inside this, that is hash 5. Hash 5 indicates that this AND gate has got a delay of 5 units, and here this OR gate has a delay of 4 units. So hash 4. So the expression is A dot B, A and B or C. Okay. So A and B, the output is E. E is the intermediate signal. So here, this is the program. I hope there is no problem in understanding the program. So the block, the module is D. So module D, and the terminals are the ones which are going to interact with the external environment, out, comma, A, comma, B, comma, C. So out is output and A, B, C are inputs. And I have one more intermediate signal, that is E. So it is declared as wire E. Okay. Now it's gate level modeling, that is AND. The AND label, the instance label I have given as A1 for the AND gate, and output is E, and the two inputs are A and B. So this is known to you. Only additional thing here is hash 5. So delay we have included in the program. Okay. Likewise, OR gate, O1 is the instance label, out, E, comma, C are the two inputs, and here we have specified the delay of the OR gate as 4. So hash 4. So remember, here we are not specifying whether it is a minimum delay or typical delay or maximum delay. It only one delay is given, so it is the same for all the values. For your reference, I have included the circuit diagram once again. This is the stimulus block, module stimulus. The name of the module is stimulus. This design has got 3 inputs. I have declared A, B, C in caps, uppercase as a register, and one output out. I have declared that as wire. This is the instantiation of the design block. The design block is D. D1 is the instance label, and if you recall, in the module definition I have first included the output followed by the 3 inputs. So the same thing I am following here, out, comma, A, comma, B, comma, C. So that is, I am connecting the ports by order. Next is the initial block. As you know, initial block is the one which facilitates sequential execution. The statements that is to be executed sequentially should be enclosed between the begin and the end statements. So the first line says A, B, C, all three I have initialized to 0. There is no time specified here. That means at time t equal to 0, I am initializing A, B and C, all the three inputs as 0. So the same thing you can see that is reflected in the waveform ABC. At time t equal to 0, I have initialized to 0. Now what happens when A and B both are 0, 0? The output of this AND gate will be 0. But this AND gate has got a delay of 5 time units, and hence this E is not defined in the program here, but I have shown in the waveform such that it is easier to visualize. So at 5 time units from the application of the input, the output E will be available. So 0 plus 5, only at 5 E will be available. Till then, till 5 time units, E is not defined. It is uninitialized or unknown. So at time t equal to 5, the E will become equal to 0. Now here, this is applied to the next OR gate. And C was already applied at time t equal to 0 to this OR gate. But there was no output till this was available because C is 0 and 0 is the non-controlling input. I hope you remember about controlling inputs. Controlling inputs are the ones when you apply that, irrespective of the other input, the output will be given. For example, for OR gate, the controlling input is 1. If any one of the input is 1, the output will be 1. So it will not wait for the other input at all. Irrespective of the other input, output will be 1. Same is the case for the AND gate. For the AND gate, the controlling input is 0. If any one of the inputs are 0, the output is 0. So irrespective of the other input, the output will be given as 0. So here, since C is 0 and that is the non-controlling input, the OR gate will wait for the second input to occur. So the second input, that is E, will only occur at time t equal to 5. So 0 and 0, output is 0. So this has a delay of 4 time units, and hence the output will be available only after 5 plus 4, that is 9 time units. So at 9 time units, the output will be 0. Okay. Now the second input that is applied is #10 A, B, C, all three are 1. #10 means the previous time was 0. This is after 10 time units, that is 0 plus 10. At 10 time units, all three inputs A, B, C will be applied as 1. So what happens now for the output? A and B both are 1 at time t equal to 10. E will be available at after 5 time units, that is 10 plus 5, that is 15. But if you see what happens to the second gate, C is applied as 1 at time t equal to 10. So this one is a controlling input. Because of this, it will not wait for the other input to occur, which will happen at time t equal to 15, but this will give out the output at 14 only. This is because C was applied as 1 at 10 time units. 10 plus 4, 14. At 14 only it will give out the output as 1. So till then, till the delay, the output will be same as the previous output. Okay, so here till 15 E is same as previous, that is 0 only. Similarly here at till t equal to 14 the output will be same as the previous output. Next input is #10. A is 1, B is 0 and C is 0. So #10 means 10 after 10 time units from the previous time. So previously it is at 10. 10 plus 10 is 20. So at 20 this will be applied. A1, B0 and C0. So we'll see what happens to the waveform. So till 20 the previous inputs only are retained, that is 1, 1, 1, and the output that has been obtained for these inputs will be retained till 20. Now at 20 A is retained at 1, B is 0 and C is 0. So A and B both 1, 1, 0. So output will be 0. So this will be applied obtaining only after a delay of 5 time units, that is 20 plus 5. So at 20 plus 5, that is 25, E will go to 0. Okay. Now C is 0. As I have told you, this is the non-controlling input. That is why C was applied at 20, but at 24 you will not get the output. 20 plus 4, delay is 4 here. At 24 you will not get the output because this is the non-controlling input. It will wait for E to occur. E will come only at 25. At 25 E is 0. It is becoming 0. So 0 and 0, output will be 0. So this will happen only after a delay of 4 time units. So E came at time t equal to 25. So 25 plus 4, only at 29 the output of this effect of this will be reflected at the output, that is output will be 0. Okay. So #20, this will go on till next 20 time units, which is not shown here in the waveform. It will be the simulation will be terminated. Okay. So this is how we visualize or analyze the circuit with the delays. In this video, we have seen different types of delays and a delay example. We have seen the effect of incorporating delay in digital circuits through Verilog program. Thank you.